thank you. Thanks first for organizing this wonderful workshop. And so I'll tell you a little bit today about my work with Dražen, who already gave a talk, so you already met him. So this is a work in progress, and it's almost finished, so we hope to have this paper out next week. Oops. Is this, how do I move this?
No, right now?
Oh, yeah.
Okay.
And just for general motivation, what kind of questions we would like to understand for when we quantize fields on curved backgrounds. We would like to understand quantum loop corrections in curved backgrounds, and in particular in cosmology, if you are high. And what we already know from various examples is like it is often when you do loop calculations, you get something which we refer to as secular effects, namely the effects that grow in time. In cosmological spaces such as the sitter, these effects grow logarithmically in time, in the sense as powers of logarithm of the scale factor. On more general spaces, they can actually grow differently in time. And of course, if you now transfer this to spatially dependent cases, such as black hole backgrounds, you would expect certain effects that behaves with the position as a secular, right? And if you really want to make any progress towards understanding these type of effects, we have to calculate perturbative effects, and in particular, we are interested in various quantum fields. But then, for cosmology, we are interested in perturbative quantum gravity because we have a lot of data available, namely CMB and large-scale structure. That's what we believe sources it. Of course, also black holes for other reasons. At the moment, we have no observational data to support it, but lots of theoretical motivation. Oops, I don't know. Maybe.
Try again. Wait. Now?
Try now. Yeah.
Okay, sorry.
Okay, so what I'll do, the structure of my talk will be, I'll give you some very rough overview of what we actually know. How do I know there are secular effects, right? And if you, these secular effects are often reflected in loop calculations, but they already have their seeds in what we call the propagators, right, which are building blocks for perturbation theory. And in particular, so if you look at the Dirac theory, you know it's scaling invariant, right? So it's a conformal theory. And nevertheless, the Candelas and Rain propagator for the Dirac fermion exhibits somehow a rather non-trivial dependence on the scale factor. So already there is a rather peculiar breaking of a scaling symmetry. And then what we already heard today is like by Falaci and Allen, they realized that massless Minkowski scalar propagator must also break this symmetry, and the propagator for dim reg was actually constructed by Emily Woodard. And what you have heard today is that surprisingly, in this very natural gauge, namely general covariant Fermi gauge, also the photon propagator in the gauge sector breaks also the sitter symmetry. And the graviton propagator, which is probably the most important, breaks the symmetry in all gauges. Oops. I think I am stuck. Maybe. Just switching this one. Okay. Now, these things that I've told you about, these are secular effects in the sitter, and of course you can ask the following question: these secular effects in the sitter space. Once we understand quantum field theory in the sitter, have we understood everything on relevance cosmology? And I think the answer to this question is, well, in more realistic inflationary space-times, which deviates from the city expansion, there might be other secular effects. And why do we know that? Well, we know that because actually, if you look at the inflaton fluctuations, which is the field that drives the inflation, it actually at bilinear level couples to gravitational perturbation. So there is a non-trivial coupling between scale and graviton. And this coupling is proportional to the slower parameter epsilon, which is the rate of change of the Hubble parameter. So in the limit of the theta, this information is completely lost. So obviously, if you want to understand realistic inflationary models and secular effects or strong effects that are potentially observable at late times, and we want to do it for the gravitons or for the inflaton, we actually have to do it in the space-time that have this epsilon non-zero. So, and these are typically the space-time when the Hubble rate is decreasing slowly in time. And of course, gravitons are hard. So let's try to do it on something simpler. So the scalars are the next best thing to do. And we now have the propagators for masses and massive scalars in constant epsilon spaces. And we also know this massive, and it turns out I'm being involved in all of these projects, as you can see. And now we also have the graviton propagator in some simple gauge and massive scalar propagator in the unitary gauge in scalar quantum electrodynamics. This was the only gauge which actually we could solve this problem for now, and it took us quite a while, and we constructed this propagator. And now the question is, what is the simplest possible calculation with this propagator that you can do? So in this theory, we have a scalar propagator, we have the photon propagator. Let's do some simple calculation. And so this, but before I do that, I'll just give you an example. Sorry?
Thanks. Sorry.
Yeah.
Continue. Keep going.
So I'll just give you a simple example of what kind of effects you can actually get. So here epsilon is again the rate of decrease of the Hubble parameter, and oops, oh, one. I think I jumped you, right? I'm sorry, I don't know how that happened. Yeah, this one. So so here what you see, this was a paper Janssen et al. And basically, if you consider just you have a non-minimally coupled scalar field, and you put it in lambda phi to the 4th theory, and the field is going to roll down the potential. And in fact, it's going to roll down potential in some kind of attractor solution. And this attractor solution is given by solving this equation. And you see, if this quantity here is negative, the prefactor, then it's going to be non-trivial solution. And that's going to be the classical solution. So the classical solution are going to have some classical condensate, which will be proportional to Hubble rate. Now, what happens if you calculate one loop correction? So you get something which we in this paper refer to as the Hubble effective potential. And if you plot it in units of Hubble parameter to the 4th for some choices of parameters, you get that the potential has a symmetry breaking form at early times. And then at some point in time, which is about n-4, in this case, the symmetry gets restored. So in other words, the quantum effects have a symmetry restoring potential here. So something rather qualitatively changes in the potential due to the quantum effects. So quantum effects can be, therefore, very important. And moreover, what we notice there, even though the scaling solution here, you know, phi is proportional to h, persists for all times classically, quantum mechanically, this gets broken by so the scaling solution gets broken by quantum mechanics. So I introduced the theory that we are using. This is my scalar electrodynamics. Of course, it has a compact scalar field, self-coupling, and it has a photon field, and it has the condensate for xi less than this. So xi is typically either small, suppressed by epsilon, or negative in this theory. Negative xi means naively tachyonic field. But actually, in this theory, the field, a scalar field is actually not tachyonic because the mass is a linear combination of two contributions, which sum up to positive. Now, for this theory, therefore, a scalar field has a positive mass, and you can actually exactly solve it. And the scalar propagator is proportional, it turns out, to the hypergeometric function. And the only non-trivial change with respect to the zeta propagator is actually in the prefactor, which is the product of two time-dependent Hubble parameters. But other than this, it looks very much like the scalar propagator for the massive field. Now, this is the scalar propagator. What about the vector propagator? Well, and this is the propagator we constructed in this paper. As you see, if you remember, Dražen actually showed you the de Sitter propagator. The Sitter propagator contains C1 and C2, which are function of y only, and these two tensor structure functions. So the first line was that. But here, the propagator in this unitary gauge depends not just on the distance function y, but also on this parameter log AA prime. And this dependence actually breaks dilation symmetry, just like in the case of scalar. And this breaking is much less subtle. You know, Dražen was trying to explain how subtle it is in the Sitter, but here is actually not subtle because it has this C3 function and C4 function, and this C1, C2, C3, and C4 in general also depend on U coordinate. And I will just say what also Dražen emphasized in his talk is that in the limit d goes to 4, you should somehow restore conformal photon. And indeed, you see U here dependence actually signifies breaking of conformal symmetry, and any breaking is proportional A to epsilon, which means in the limit when epsilon goes to 0, which is a Sitter, it drops out, but also d minus 4, which means in the limit when you are in 4 dimension, you're back to the conformal limit. Now you can say, well, why should I care if in d equals 4, I get a conformal photon? Why should I care about all of this? Well, the reason is because this d minus 4 proportional corrections, when you calculate loops, can lead to secular effects, which are finite. And therefore, they're actually crucial. They actually contain physical information. And so anyway, so let me now, so in what follows, I will actually tell you what is one of the maybe, well, there are several questions we wanted to answer. One of them was, you know, when you calculate this energy momentum tensor one loop order, remember energy momentum tensor is the tadpole associated with the graviton. So this curly line is the graviton coupling to scalar loop and to the vector loop. And this is the counter term because of divergences. And we did this calculation with our propagator and we got non-conservation. We thought the propagator was wrong and broke our head. And then Dražen had the idea, maybe this is not the complete story. Maybe we are missing something. And indeed, we are missing the contribution from the scalar condensate. And so there is a classical scalar condensate. And of course, to the classical scalar condensate, there is a tadpole-like contribution, the quantum condensate. And these are the results. I will not try to explain them, but I will emphasize that both of these results from the scalar and the vector loop contain this logarithm, which, because of the dependence on the scale factor of AH, actually contains secular behavior. So it grows as logarithm of the scale factor. Notice in the limit when epsilon goes to 0, this is gone. So again, this is an effect that is not there in the Sitter. And so now we know that actually the energy momentum tensor acquires the contributions of such a tadpole, scalar and vector. And when you add these two, wonderfully, you get the conservation. So the lesson here is that in these curves backgrounds, in the presence of these condensates that are space-time dependent, one has to be careful when you actually calculate the energy momentum. And now the total energy momentum tensor, the scalar and vector contributions are actually conserved. And of course, they also have the same kind of secular behavior as the scalar condensate, namely logarithm h of a mu. And this secular behavior, just like before, grows with the scale factor and disappears in the city limit. So, so here there is one interesting limit that you can consider, namely when q squared is much greater than lambda, and that's the limit when this prefactor becomes much greater than 1, and this is the limit when at late times also this secular behavior can become big. Okay, and this is this white region, so it becomes more and more white, which means on this plot's larger and larger. So, and maybe I wanted to say one more thing, is that this secular behavior that we have observed here actually spoils perturbation theory. Why? Because when these logarithms became large, when the logarithms became large, then even the coupling constants are small, perturbation theory is broken. Of course, you know from RG that you can actually resum these logarithms by solving the RG equation for the coupling constants, and similarly for other objects such as one-point function, energy, momentum tensor, etc. The question is, can we actually resum these logs as well? And I think our proposal here is yes. And the reason is because these logs appear in similar fashion as in cases in flat space. The difference is like the scale mu couples now to field that is space-time dependence in this case. In more general cases, space-time dependent. So then this reference scale mu that is normally attached to some physical scale, in this case can be identified to time-dependent field which has this form, and then indeed you can now solve the beta function equation and resum these logs. That's our proposal. And to conclude, I would just say that this sort of opens the possibility to resum these logs that appear as a result of quantum effects and breaking of scaling symmetry. And but the physical origin of these logs is actually that the coupling constants in the presence of these background fields can get stronger or weaker as a function of time or space. And that's what this physics is telling us. But I should also emphasize that we have not touched the renormalization. Renormalization we are doing exactly in the way that everybody else does it. So, and finally, since this is, you know, you have to do PR a little bit of every research. So there is impact of this work on society. We expect, as you see, some people already heard about this work and started buying T-shirts, and now the new word has appeared. It's already there in the Urban Dictionary. Tadpole means a young man that goes with an older woman, as well as an unavailable person with low mental capacity. And the curious example of Urban Dictionary, so they obviously knew about this conference because they say, I have a huge tadpole in my Spanish class. Anyway, so that's the end of my talk. You can read the conclusions, and thank you for attention.
Thank you very much. Time for questions. Any question for the audience? Okay. So I can ask maybe a very short question. In the first slide, you said something about phenomenological implications, like
yeah.
Where do you think it can be relevant? For example, in the power spectrum in cosmology or something like that?
Yes. So I think at the moment it's a little bit too early to know whether these kind of effects can have any ramifications on in cosmology. But here is one example of recent calculation where quantum correction to potential, which means local gravitational fold by the graviton loop in a certain gauge goes as G squared, which is 10 to the minus 12 in inflation, times log cube, which is about, I don't know, 100,000. So you know, this is one loop, 100. You know, the suppression of GA squared is actually enhanced by 100,000 factor. So, so of course, we don't know, this is a gauge dependent answer, we don't know
Okay.
how sure that is, but it's potentially observable.
Okay, thank you for your answer. Okay, I think we have another question.
How do you identify the arbitrary scale? I mean, what are the arguments to identify the arbitrary scale mu naught that you have?
You have to do the calculation, right? And so what we've done here is one loop calculation, and we identify what's the logarithm that generates. So if you actually look at the structure of the log, the structure of the secular terms, for example, for the task form, for the scalar task form, right? It has this structure here. Now this two things together in the limit when the masses are light, is basically log h. In the limits when masses are much greater than h, it just becomes the standard flat space log. That's why I didn't discuss it here. We discussed it in the common paper. So so actually the theory tells you what is the log you need to resum. And we have not calculated two-loop expansion. So in order to really confirm this hypothesis, that the scale, this is the reference scale I was talking about. Yeah. In order to confirm the hypothesis, this is the right reference scale, we will have to calculate two-loop and show that it does match to this. And then we will be sure, by experimentation that this is the technique that works.
Okay.
Okay, thank you.
Thank you. So I think maybe let's thank the speaker again.